So, good day everyone. Uh, my name is Dairo and I will be reporting about the evaporation from free surface. So first is the Penman method. So Howard Penman in 1948 devised a semi-empirical method for estimating the evaporation rate from free water surface, which combined energy, budget, and mass balance equations. So E sub O is equal to the quantity delta over gamma multiplied by H plus E sub A all over delta over gamma plus 1. So, uh, where EO is the potential evaporation rate expressed in millimeters per day, and delta over gamma is the empirical parameter depending on temperature, and H is equals to 0.95 Ra multiplied by the quantity 0.18 plus 0.55 lowercase n over uppercase n minus RO, and E sub A is 0.35 multiplied by quantity 0.5 plus U sub 2 over 100 multiplied by the E sub A minus E sub D. So RO, which is also the outgoing radiation, is expressed in the equation sigma multiplied by dA raised to 4 multiplied by the quantity 0.56 minus 0.09 multiplied by the square root of E sub D multiplied again by the quantity 0.10 plus 0.9 lowercase n over uppercase n, where E sub D is the actual vapor pressure, E sub A is the saturation vapor pressure, and U sub 2 is the wind speed in miles per day, and RH is the relative humidity. So lowercase n over uppercase n is the ratio between the actual sunshine and possible sunshine hours, which can also be estimated by cloudiness. So this is a table that can be used to determine the R sub A, which uses the latitude on the northern and southern hemisphere with their corresponding values in different months. So the lines in the west to east directions are latitudes, or east to west. So and if you're wondering, north to south is the altitude. So this is a table used to determine the sigma T raised to 4, which is expressed in millimeters of water. So the air temperature and saturation vapor pressure, which is expressed in millimeters of mercury, depending on the temperature also. So the weighing factor, or the delta over gamma, which also depends on temperature. So there's also a simplified version of Penman's formula using temperature data alone. So E sub O is equals to the quantity 700 Tm over 100 minus A plus 15 multiplied by the quantity T minus Td all over 80 minus T. So Td mean the mean dew point, which is expressed in T minus quantity 100 minus RH all over 5, and A, which is the latitude in degrees, Tm, which is the temperature plus the 0.006 multiplied by H, where T is the mean temperature and H is the elevation in meters. So there are there are only two empirical equations for evaporation estimation in this presentation. So first is the Meyer's formula, which is expressed in E sub L equals to K sub L multiplied by quantity E sub W minus E sub A plus 1 plus U sub 9 over 16, where U sub 9 is the monthly mean wind velocity in kilometers per hour at about 9 meters above ground, and the K sub M is the coefficient accounting for various other factors, which is equals to 0.36 for large deep waters, 0.50 for small shallow waters, and E sub W is the saturation vapor pressure at the temperature of water expressed in millimeters of mercury, and the E sub A is the actual vapor pressure in the air expressed in millimeters of mercury. So lastly is the Roche formula, which is developed at the same time as the Mayer's 1915. So it is expressed uh, as E sub L equals 0.771 multiplied by the quantity 1.465 minus 7.32 times 10 raised to negative 4 Pa multiplied by the quantity 0.44 plus 0.0733 U sub O multiplied by the quantity E sub W minus E sub A. Where Pa is the mean barometric pressure reading in mm of mercury. So barometric pressure is also equal to 1 atm or 1 atmospheric pressure. So U sub O is the mean wind velocity in kilometers per hour at ground level, or 0.6 meters. So example problem. So I have only one example problem, but I will use the three equations. So a reservoir with a surface area of 250 hectares had the following average value of parameters during a week. Water temperature is 20 degrees, relative humidity 40%, wind velocity at 1 meter above ground is 16 kilometers per hour. So estimate the average daily evaporation from the lake and volume of water evaporated from the lake during that week. So using Penman's equation, Penman's equation is the simplified version. So first we get the dew point, which is equals to 20 minus quantity 100 minus 40 divided by 5, 40 which is the relative humidity. All of this equals to 8. So the T sub m is equals to 20 plus 0.006 times 1 meter, which is equals to 20.006. So since the latitude is not given, we assume 10 degrees from the equator in the northern hemisphere. So therefore, E sub O equals to 700 multiplied by 20.006 divided by 100 minus 10 plus 15 multiplied by 8 all over 80 minus 20, which is equals to 4.59 millimeters per day. Since the problem asks for water evaporated from the lake during that 1 week, so we convert. So converting 4.59 millimeters per day, we get 80,225 cubic meters per week, which is the evaporated volume. So using Mayer's formula, so first is kinuha niya yung water vapor pressure, which is 17.54 millimeters of mercury in 20 degrees Celsius. So, tapos yung sa air is multiply mo lang yung value ng water vapor pressure ng relative humidity, so equals to 0.02 millimeters mercury. So the U sub 9, the wind velocity at a height of 9 meters above ground. So U sub 1 is equals to 16 kilometers per hour. So we need to determine U sub 9. So using the 1/7 power formula, so U sub H is equals to C, where C multiplied by H raised to 1 over 7, where C is constant. So U sub 9 over U sub 1 equals to C multiplied by 9 raised to 1/7 all over C multiplied by 1 raised to 1/7. So 1 raised to 1 over 7 is just equals to 1, and the C in the numerator and the denominator will cancel out. So leaving us with U sub 9 is equals to U sub 1 multiplied by the height 9 meters, so 29 kilometers per hour. So by Mayer's formula, E is equals to 0.36 multiplied by the quantity 7.54 minus 7.02 multiplied by the quantity 1 plus 21.9 over 16. So all of this equals to 8.97 millimeters per day. So the evaporated volume in 7 days is 7 days times 8.97 millimeters divided by 1,000 to get meters, multiplied by the area. So 250 hectares is multiplied by 10,000 square meters. So therefore the evaporated volume will be 157,000 cubic meters per week. So lastly, using Rower's formula, same process as Mayer's, we get the water vapor pressure, which is 17.54, and the air vapor pressure 7.016. And since usable is equal to 0.6 as per required in the Rower's formula, and U sub 1 is 16 kilometers per hour. So therefore U sub 0.6 is just equal to 0.6 raised to 1 over 7 multiplied by 16, which is equals to 14.87 kilometers per hour. So therefore E sub L, or the evaporation rate, is equals to 0.771, 1.465 minus 7.32 times 10 raised to negative 4 multiplied by 760 times 0.44 plus 0.0733 times 14.87 times 17.54 minus 7.016. So E sub L is 11.3 millimeters per day, and we need to get the evaporated volume per week. So converting, we have 197,750 cubic meters per week. So next is the direct measurements of evaporation estimation. So first we have atmometers. So they measure the loss of water from a wetted porous surface. So the wetted surfaces are either porous ceramic spheres, plates, or exposed filter paper disc saturated with water. So this device stands at around 1.5 to 2 feet or 0.46 to 0.61 meters tall with a diameter of 3 to 4 inches, which is approximately 76 to 102 millimeters. So water is drawn from the water reservoir through the tube to wet the plate. As the water on the plate evaporates, more water is drawn from the reservoir to wet the plate. The plate should be placed in direct sunlight so that evaporation rates are not affected. It should not be placed near tall trees or buildings, as they can affect the amount of exposure. To measure the amount of water that has evaporated, calculate the change in water level on the gauge by subtracting the final water level from the initial water level. So this is self-explanatory, and we have advantages and disadvantages. With its advantages, having low cost, easy operation, convenience, no computer or power required, so manual. So disadvantages is a potential weather damage can occur to the device, constant need to refill the water supply, gauge must be read manually, only on manual model. So next is the Pichet evaporometer. Pichet is the most commonly used in the Philippines. So it is a porous paper-weight atmometer. So the instrument consists of a graduated tube closed at one end that is filled with distilled water and then covered with a larger circular piece of filter paper held in place by a disc and collar arrangement. So in operation, the instrument is inverted so that the distilled water is in contact with the filter paper. The amount of evaporation that occurs during an interval of time is determined by noting the change in level of the meniscus of the water. So same as the atmometer previously. So this is it. So distilled water yung so class A evaporation pan, a cylinder with a diameter of 47.5 inches or 120.7 centimeters that has a depth of 10 inches or 25 centimeters, 1.0 inch. Okay. The pan rests on a carefully leveled wooden base and is often enclosed by a chain link chain link fence to prevent animals drinking from it. Evaporation is measured daily as the depth of water in inches evaporates from the pan. The measurement day begins with the pan filled to exactly 2 inches, 5 centimeters from the pan top. At the end of 24 hours, the amount of water to refill the pan to exactly 2 inches from its top is measured. So, same pa rin, yung kinukuha lang yung difference ng water na nag-evaporate. So, this is an example of evaporation pan class A. So, it has medyo makalapit lang yung dimensions. Yung sa diniscuss ko is 120.7 centimeters. Ito is 121 centimeters and a depth of 25.5 centimeters. So lastly is the sunken Colorado pan, which is a square 0.92 meters or 3 feet on a side and 0.46 meters on the other side, and 0.46 meters deep and made of unpainted galvanized iron. As the name suggests, it is buried in the ground within about 5 centimeters of its rim. Evaporation from a sunken Colorado pan can be compared with a Class A pan using conversion constant. The pan coefficient on an annual basis is about 0.8. So, as you can see, naka-bury siya underground from 2 inches from its top. And that is all. Thank you. And these are my references.